Okay, so let me go ahead and start. Welcome back, everyone. So last time, what did we cover last time? Ooh, op amps. Okay, op amps or operational amplifiers. And we're gonna let's see. What did we learn last time? We saw the voltage follower, right? Whatever voltage we put in, we get out of it. So that was one useful thing that we've already learned that we can do with an op amp. So there was the voltage follower. And so there were some rules that we learned that really help us to analyze any op amp circuit that we're going to deal with. And there's really only two rules that we kind of have to pay attention to. And that first rule was no current in or out of the inputs. No I in, out of inputs. Okay, so as we're looking at the two inputs for this operational amplifier, we have no current going in and no current going out of the inputs. So both here and here, we can say that we have 0 amps. Okay, and the second rule was that the op amp will do whatever it has to in order to make both inputs equal to each other. However, that's only applicable in the case of a closed loop configuration, which this voltage follower is. In fact, this is the simplest example of having this feedback over here, right? Where an output is connected back to an input. Anytime, and this goes for more than just op amps, anytime you see an output of anything tied back into its own input. If I have a system, black box, whatever it is, if you see an output tied back to an input, that is referred to as feedback. And there are tons of good examples of that being incredibly useful that you'll probably see and encounter as you kind of progress in computer engineering. So let's say rule number 2, only closed loop configurations op amp will make both inputs equal. Okay. And so armed with those two rules, we can analyze any of these circuits. In the case of the voltage follower, we can think of this as having a V in and a V out. And we know that V out's going to be equal to V in. And why is that? That's by rule number 2. So if I placed, let's just say 2 volts on this input, do we have a closed loop? Yes. Do I have no current flowing in or out of the inputs? Yes. And so over here, if I have 2 volts on our non-inverting input, then our inverting input should also have 2 volts on it. Why do we have 2 volts on this input? Well, it couldn't have been changed by the input. The input has no ability to affect the voltage here, but the output does. And since we have this direct connection from the output back to the input, if this is 2 volts, it was made 2 volts by this. And so we get 2 volts here. So using this really simple rule, you can go ahead and figure out that, yeah, V out is going to be equal to V in for this circuit. And then now you might go, well, okay, what's the big deal about this voltage follower? Why is it useful? Well, yeah, if you have 2 volts here, you get 2 volts out. If I have 3 volts here, I get 3 volts out. However, these inputs are high impedance, and the output is guaranteed to be low impedance. So for that reason, you can think of this as a buffer. Okay, so if I need to measure a voltage and I don't want to be hindered by the impedances, right? Just like when we were looking at that common emitter amplifier and you solved for your input impedance and your output impedance, and then you use the generic amplifier model, and then you see that voltage divider. We don't have to worry about that anymore. You don't have to calculate the attenuation, the signal drop, the voltage drop that you're going to get by virtue of having, say a medium impedance driving a medium impedance. So incredibly valuable circuit. I use this, oh my God, all the time. Every single design I've ever had, every single commercial product, every industrial product, I usually have 10 of these hanging around. And we're going to get into the whole analog going into a digital system. We're going to get to that next class. But I'll show you guys later how this gets applied to embedded systems and analog measurements by digital systems. That's really where you start to see a lot of the connection between 311 and your 262 material, your 346 material, embedded systems. Okay. So that's the voltage follower. The other circuit that we saw was the comparator, and the comparator was without having feedback. In fact, maybe the only useful circuit that you're going to see that does not have a closed loop configuration is the comparator. And the comparator, simply its output is going to saturate either to the positive rail or saturate to the negative rail, depending on which one of these is larger. Okay, so we can use that for comparing two voltages, find out which one is larger, and that's also a very useful component or configuration to use one of these op amps in. Okay, so that's what we've covered thus far. Let's go ahead and we can construct amplifiers out of this. Let's go ahead and use that name, operational amplifier. Let's get to the amplifier aspect of this. Okay, now all of these circuits are a bit like baking recipes. And I say that in terms of all of these are well defined and they have names and their equations are already written. But I will show you how the application of that second rule, you don't have to memorize these things. You'll just be able to look at one and solve for what V out is in terms of your inputs. So we're going to start with let's do the non-inverting amplifier. Okay, so what's in this name over here? Well, first off, amplification. We're making an amplifier. We're going to take a small signal. We're going to make it larger. Non-inverting. Okay. If the input is positive, the output will be positive. If the input is negative, the output would be negative. Okay. So non-inverting. We're not going to get a polarity switch of that input voltage. And now let's go ahead and draw what this looks like. Okay, we're going to have our non-inverting input at the top, inverting input at the bottom. We're going to feed our input voltage over here to the non-inverting side and our inverting side. is going to have these two resistors. I'm going to go ahead and call this R1, and I'm going to call this RF for feedback resistance and just R1. And we have a V out over here. Now, I can go ahead and give you the equation for this, and might as well. V out is going to be equal to V in times RF divided by R1 plus 1. Okay. So if you notice, our input voltage is going to be multiplied by this gain. Specifically, this refers to the voltage gain. And so, if you notice, there is no minus over here. So whatever the polarity of our input voltage is, our output voltage will be the same. And then the gain, how much amplification we're going to get, would be dictated by this part right here. And for example, let's go ahead and let's give ourselves some values over here. So I'm going to make R1 equal to 1K, and I'm going to make RF equal to 9K. And let's give ourselves some voltage input. Let's make this 1 volt. Okay, so what's going to be the output from this amplifier, from this op-amp circuit? Well, I already gave out the equation, so V out would be equal to V in. V in we set is 1 volt. And our gain would be determined by RF divided by R1 plus 1. So RF is 9K. R1 is 1K. And that's plus 1. Now 9K divided by 1K is going to be 9. 9 plus 1 gives us 10. 10 is our gain for this circuit. So we're going to always have this gain of 10. So what do we get at the end of the day? We get 10 volts. Okay, if I put 2 volts here, I'm going to get 20 on my output because I'd get 2 volts times 10 gives me 20. If I had 3 volts, I'm going to get 30 volts out. So you notice our polarity stays the same, and we get some amplification that we can adjust with these two resistances. Now, as I said before, we only really need our 2 rules to analyze this. And in this case, I had just given you the equation, but can we come up with this on our own? Absolutely. So let's go ahead and let's analyze that. Now let's go ahead and make V in. We're going to use the same values that we had. 1K for R1, and our feedback resistor is going to be 9K. And we want to know what V out is equal to. Okay, so how can we analyze this? How can we figure out what V out is? According to the equation, it should be 10. We should get 10 volts on this output over here. But let's see if our rules can help us out. Okay, let's go with rule number 1. No current in or out of these inputs. Okay, does that help us out in figuring out what V out is? Not so much. Let's see. Great. I got no current going in or out of the non-inverting input. I got no current going in or out of the inverting input. That's rule number 1. And doesn't really get us started. Okay, let's check rule number 2. Rule number 2 is, first off, we need to ask ourselves, is rule number 2 even applicable here? If we have a closed loop of any kind, yes. Now, in the case of this closed loop, notice what we've done here. We've taken the output and we've put it through this feedback resistor, and then we have another resistor tied to ground. So what are we doing here? We're taking this output and we are putting it through, it looks like a voltage divider, right? So this voltage divider pops up everywhere. So it looks like we're going to take this output and we're going to divide that voltage down. You can think about this as if you think about just this as a voltage divider. Here, I have a voltage going through 2 resistors to ground, and you're looking at the voltage at this point, right? And so you can think of this as V in, you can think of this as V out, and I guess RF would be your R1 if you're looking at the classic voltage divider equation. R1 would be R2. Again, if you were looking at the classic voltage divider equation. So we know we're going to get some voltage here that's proportional to our V in. And look at what we're doing here. We're essentially looking at both of those voltages and changing our output based off of these 2 voltages. Okay, so that's kind of overview what's going on, but rule number 2 tells us if we have a closed loop, which we do, then the op amp will do whatever it has to in order to make both voltages the same. If this is 1 volt, then that means this must also be 1 volt. Okay, that gets us started now. Now the question is, how did this become 1 volt? Because by rule number 1, it cannot be made 1 volt from this pin of the device. This pin of the device has no ability to influence the voltage at this point. That's what it means when we have no current in or out of something. You can look at this pin as just looking at the voltage, just measuring the voltage, not actually changing the voltage, okay? High impedance or no current in or out. So how did this become 1 volt? Well, it became 1 volt because this output did something here. And our job is to figure out what did this output do. Okay, so now we can go ahead and we can find out what's happening in this whole path. We know that this should be 1 volt by rule number 2. Now, let's go ahead and start working our way backwards to V out. I have 1 volt here. What's my voltage at this point? It's 0 volts, right? That's what it means when you have a ground symbol. I have 0 volts here. I have 0 volts here. I have 1 volt here. Doesn't current always flow from a high voltage to a low voltage? All right, so I know I have current flowing through R1. So now I'm just going to use all of my basic 211 rules to analyze this. What's my voltage drop across R1? Well, it's 1 volt, right? I have 1 volt here, I have 0 volts here. I have a total 1 volt drop across this resistor. So VR1 is equal to 1 volt. Can I use Ohm's law to figure out what this current is? Absolutely. Let's go ahead and do that. Let me pull up my calculator here. Put this up here. I have 1 volt across a 1K. So 1 divided by 1,000. I think this is going to be 1 milliamp. Yeah. Okay, so I have 1 milliamp flowing through this resistor. Now, where did this 1 milliamp come from? Well, look what we have here at this node. I have 0 amps coming in or out of this wire, and I have 1 milliamp going this way. Kirchhoff's current law, right? The sum of the currents entering a node must equal the sum of the currents leaving that same node. So if I have 0 amps going in to this node, and I have 1 milliamps leaving, then I must have 1 milliamps going through our feedback resistor. Cool. Okay, so now I know I have 9K here and I have 1 milliamp flowing through my feedback resistor because I used Kirchhoff's current law to get at that 1 milliamps here. So now can I figure out the voltage drop across RF? Well, I know the current going through it. I know the resistance of it. I got 2 of my 3. Let's go ahead and solve for VRF. VRF, therefore, is going to be equal to, well, V equals IR. So 1 milliamp times 9K. Let's figure out what that is. 0.001 times 9,000. I think it's going to be 9 volts. 9 volts is what we get. Okay, so I get a 9 volt drop across my feedback resistor. And notice the direction of current. Current always flows from a high voltage to a low voltage. Okay, and I have 9 volts as I drop from this side to this side. Well, what do I have on this side? I have 1 volt, right? So now I'm just using Kirchhoff's voltage law. If I have 1 volt here and I dropped 9 volts to get at 1 volt, then I must be 9 volts higher than 1 volt. In other words, I'm at 10 volts. And I'm at 10 volts everywhere along this wire, so my V out is equal to 10 volts. Okay, so I got the same exact answer as if I was using my equation, except I got there using only my basic rules and my knowledge of op-amps, which were just those 2 rules. And I get at this same answer, okay? So that's generally how you analyze these circuits. You use rule number 2 to tell you what the voltage on these pins are, and then you go ahead and follow the circuitry to get back at what V out is. Okay, so that's the non-inverting amplifier. So if you need a gain of if you need a gain of anything higher than 1, you're good. 2 volts, 3 volts, 4 volts, or I shouldn't say volts, gain 2, gain of 2, gain of 3, gain of 4. If I need to make a small signal larger and I want to make sure that that signal does not get inverted, then this is your go-to first choice for constructing an amplifier out of an op-amp. Okay, cool. Any questions about this? All right, let's go on to the next op-amp circuit. Our next op-amp circuit is the inverting amplifier. Okay, the inverting amplifier. So same, similar thing. We're going to get some amplification. However, going by the name, it looks like we're going to get a bit of a polarity switch here. So if we have a positive voltage on the input, we're going to get a negative voltage on the output, and vice versa. So what does this circuit look like?
So, Professor, that's the schematic symbol for an op-amp?
Yep. Yeah. The only thing I'm leaving out of it for all of these examples and circuits, I have left out the positive and negative rails. So how you power this op amp, I have left out. I am working off of the assumption that I am powering it and I'm keeping my inputs and outputs within those power rails. So in the case of like over here, I'm working off of the assumption that I have a plus something that's larger than 10 volts and a minus, this could be 0 volts, this could be minus 5 volts, but I have two power rails.
All right, gotcha. Thanks, Professor.
Cool, yeah. Okay, so here's our inverting amplifier. Now this is kind of neat because if you notice, I still have feedback. I have it over here, but it's going back to that same pin that I'm feeding my input voltage to. Well, what's going on with the non-inverting input over here, this plus input? That's tied directly to ground. So this is going to be 0 volts. So if this is 0 volts, what's this op amp going to do? It's going to try to make this 0 volts. Again, rule number 2. So what is the equation for this? Well, V out is going to be equal to V in times minus RF divided by R1. And so our gain now is going to be a minus RF divided by R1, and that's multiplied by our input. We're going to end up with this negative symbol here on the gain. So we are going to get an inversion. If I have a positive on V in, I'm going to get a minus on V out, and vice versa. But let's go ahead and let's give ourselves some values here. Okay, let's say V in is going to be 2 volts. Let's make R1 equal to 1K. Let's make RF equal to 1K. Okay, so according to the equation, V out should be equal to 2 volts Well, 1K divided by 1K should be 1, so we have a gain of 1. However, we have that minus sign here, so it's minus 1. So 2 volts times minus 1 gives us minus 2 on our output. Okay, is this true? Let's go ahead and redraw this. We have 2 volts here, and we're supposed to get -2 on the output. Let's go ahead and analyze this. Okay, rule number 1, no current in or out. Does that help us right now? Not really, but it will help us in a minute. Rule number 2, op amp, let's see, do we have a closed loop? Absolutely. We have a connection from V out back to our inverting input here. So notice now the feedback is over here tied to the inverting input, as opposed to the previous example where we had the output going back to oh no, sorry. The previous example, we had the output tied back to the inverting input. The difference was that we were applying our voltage to the non-inverting input. That is not happening here. We are applying our input voltage to the inverting side. Okay, so that's one of the major differences. Okay, so does rule number 2 help us? Do we have a closed loop? Yes. So that means both voltages must be equal to each other. This is directly tied to ground, so this should be 0 volts. And the op amp will do whatever it has to make this 0 volts by virtue of changing the output. Okay. Now we can go ahead and use our basic rules, trace this back. Current always goes from a high voltage to a low voltage. And I know what my voltage drop across this R1 is. I have 2 volts on one side, I have 0 volts on the other side. I have a 2 volt drop across it. So can I figure out what this current is? Well, I have 2 volts across a 1K ohm resistor. So 2 volts divided by V equals IR, right? So 2 volts divided by 1K gives us 2 milliamps. But notice no current in or out of this input here. So this 2 milliamps is entering this node. So I better have 2 milliamps leaving the same node. Kirchhoff's current law. Okay, does that now let us figure out what the feedback, the voltage across the feedback resistor is? Absolutely. VRF, therefore, is going to be equal to, well, just use Ohm's law. It's going to be 1K times 2 milliamps. Two volts. Now, let's make sure that we interpret this correctly. Current always flows from a higher voltage to a lower voltage. This side must be less than this side. This side's at 0. This must be less than 0 volts. By how much less? By 2 volts. So this, therefore, is minus 2 volts. Therefore, V out's equal to minus 2 volts. Okay, so not bad as long as we keep track of our rules, we apply them correctly, and most importantly, let's not mess up those basic 211 rules. Current always flows from a higher voltage to a lower voltage. In no other world does that ever change. This side is always positive, this side's always minus, at least as far as conventional current's concerned. So let's make sure that we always keep that in mind. Kirchhoff's current law helped me out here. And then for the voltage drops, Kirchhoff's voltage laws, and then, of course, Ohm's law. But the real trick to starting this one was recognizing that this is 0 volts and that by rule number 2, this must be 0 volts. Okay, now a little added tip in here. This junction has a name. We actually refer to this as a virtual ground. Now, I say this because you're going to see this if you're ever looking up about op amps. Now, in the grand scheme of things, my take on it is, okay, big deal. So what? Okay, you're calling this a virtual ground. This is a virtual ground, or called a virtual ground, because it is at the same voltage as ground without actually being connected to ground. Now, does that do anything for us? Not really, but I guess it's good to know, and you'll encounter it. So that's just my take on it. This is 0 volts. It's, for all intensive purposes, ground, and current will flow to it. So yeah, that's the inverting amplifier. Now, one other note about these two. Notice a limitation that I have here. With a non-inverting amplifier, my gain has to be larger than 1. Okay? Anytime I have a gain of 1, a gain of 1 is unity. We call that unity gain. So in this case, the gain over here is referred to as unity. And so the non-inverting amplifier, as nice as it is to have an amplifier I cannot get unity gain out of this. I really cannot, practically speaking, pick values for these resistances such that give me 0 in this. You could try. You can go ahead and put a, let's see, what would you do? Put a big resistor on R1, put a very small resistor on RF, and this circuit's going to not work due to some practical limitations of dealing with real op amps. So even though in our ideal sense on a board, it might work out to get something very small here, like a gain close to 0 and then 0 plus 1, and then you're like, hey, I have unity gain, and it's non-inverting. It doesn't work that way. And so you're really limited to gains above 1. Over here with the inverting amplifier, you can have unity gain as I did over here, as long as you pick your values to be the same. However, you do get an inversion, okay? So your polarity does swap. So that could be a drawback of an inverting amplifier. Now, that being said, many times if I have an amplifier, like, I don't care if the signal is inverted. If you're listening to your music, your ears do not care if that if the sine wave went negative before it went positive, or vice versa. It really doesn't matter. So that one is application dependent. If I have a sensor and I'm tying a sensor to an embedded system or any type of digital device, and I'm going to take measurements, I may care about the polarity. So just keep that in mind. The inverting amplifier is nice because I can get gains that are either 1 or very close to 1, but they are inverted. And I have a non-inverting amplifier that cannot have a gain of 1. Okay, someone help me out here. I really want a non-inverting amplifier that has a gain of 1. Okay, I really want one. I just do. I don't know why. How can I make one? This is my coffee break. Did we see one already? Maybe yes, maybe no. Maybe in a previous class. Maybe earlier today. Non-inverting unity gain amplifier. I want a gain of 1. Come on. Someone's got to catch on to this. Where was it? It was earlier today. What did we see? We saw the non-inverting. And then before that, we saw the inverting. Before that, we saw a comparator. And before that, we saw a voltage follower. Huh? Right? Voltage follower has a gain of 1. Yeah, my voltage follower is a non-inverting amplifier with a gain of 1. Unity gain. So, there's actually another name for the voltage follower that I did not mention, or maybe I did mention it. Voltage follower. What was the other name for a voltage follower? Analog buffer. Or non-inverting unity gain amplifier. That's a mouthful. Okay. Voltage follower, analog buffer, non-inverting unity gain amplifier. All 3 names that describe the functionality of this. Voltage follower, the output follows the input voltage. Whatever the input voltage is what I will get on the output voltage. Analog buffer, okay? I am buffering those impedances. guaranteed to have high impedance on the input and guaranteed to have low impedance on the output. So if I need to buffer this side from this side, or buffer the input from the output, then analog buffer. Okay, and the last one, non-inverting unity gain amplifier, because it does have a gain of 1, which implies unity, and I am not getting any inversion. Okay, the polarity of the input's the same as the polarity of the output. Okay, so those, we have now covered 4 op-amp circuits, and we've analyzed them with only our 2 basic rules. Okay, let's do an op-amp circuit that we don't know what it does. It doesn't have a name. I'm making this one up. It's the unknown op-amp circuit. Okay, I'm just gonna make a mess here. Let's do this. I'm gonna have non-inverting, inverting. This is a problem I gave on an exam. Let's make this. Let's just make these all one. Sure, let's make them all 2K. Over here, what am I gonna have? Let's do this. And I do need an input voltage here. Let's say my input voltage is... Let's just do 1 volt. Okay, so I know nothing about this circuit. I've never seen this in a book. You won't find it in a book because it's not that interesting of a circuit that does anything really. But can we go ahead and figure out what V out is supposed to be? Yeah, absolutely. Let's go ahead and let's figure out what V out is. Okay, so this is a good test of your op-amp rule skills. Okay, what do I know about this circuit? Do I have feedback? Yeah, absolutely. I got a connection from the output back into one of my inputs. The the inverting input here is connected to the output through this whole mess of whatever this is doing. And then my non-inverting input is getting some voltage in, and I want to figure out what my V out is. Can I go ahead and analyze this? Absolutely. Let's do, rule number 1, no current going in or out of the inputs. Well, that will be useful, but for right now, that doesn't really get us very far. Does rule number 2 work? Yeah, we have feedback, so rule number 2 is applicable. This voltage will be the same as this voltage. So we need to figure out what one of these voltages is first. I have 1 volt over here, but notice I have this resistor in my path. So, does that change anything? Let's see. What's my voltage drop across this resistor? Someone type that into chat. What's my voltage drop across this resistor? Yeah, 0 volts, right? Because rule number 1, no current in or out of these inputs. Yes, thank you for typing that in. Okay, so I got 1 volt over here, but I have 0 amps in or out of this input over here. So my voltage drop across this. 0 volts. 1 volt minus 0 volts gives us 1 volt. If this is 1 volt, what should this be? Type that one into chat. If this is 1 volt, what should this be? Yeah, thank you. Okay. How did this turn into 1 volt? Well, it didn't get changed by this input. Again, this pin has no influence over the voltage at this point. No current in or out. We saw that up here. Same thing is true over here. So this became 1 volt by virtue of getting modified by our output somehow. Let's figure out how that is. All right, so I have 1 volt here, and well, check this out. What's my voltage at this point? Type that into chat. What is my voltage at this point? Yeah, right? Well, again, no current in or out of this input. Means I got 0 amps going through the 2K. If I have 0 amps going through a resistor, I get 0 voltage drop across it. And if I have 1 volt minus 0 volts, I'm left with 1 volt. Okay. So now I think I can follow this all the way back. I think that was the trickiest part over here, was realizing that this no current in or out of the inputs leads us to a 0 volt drop across this one and this one. And that's how we can follow our voltages. Does this mean those resistors are useless? No, but it's a little trickier. There actually is a little bit of leakage. There are some current. So putting these resistors in there are, yeah, I would say this resistor a little more useless than this resistor. Okay, but let's go ahead and let's follow this back. Okay, so I have 1 volt here, 0 volts over here. My current is going down. What's the value of said current? Well, just apply Ohm's law. 1 volt divided by 2,000. .5 milliamps. Okay, that 0.5 milliamps had to come from somewhere. It did not come from here. Kirchhoff's current law tells us it came from here. Now I need to figure out what my voltage drop is across this 2K. I have 0.5 milliamps times 2K. I think that's going to be 1 volt, but just to double check. One volt. Now, notice my current goes from a high voltage to a low voltage, so I know this side must be higher than this. This is at 1 volt. This must be 1 volt higher, right? Because we're dropping 1 volt across this resistor to get to 1 volt. So if you work backwards, 1 volt and 1 volt higher than 1 volt makes 2 volts. Now over here, how did this become 2 volts? Well, let's work backwards. I have 2 volts here, so I have 0 volts over here. So my current's going down through there. I have 2 volts across the 2K. So 2 volts divided by 2K gives me how much current? 1 milliamp. Okay, now I can go ahead and follow this back even further. Kirchhoff's current law, though, will tell us the current going through this 2K. I have some current entering, and I have 0.5 milliamps leaving and 1 milliamp leaving. Therefore, I must have 1.5 milliamps entering. Okay, with that, I can now figure out my voltage drop. I have 0.0015 times 2K, V equals IR, and I get 3 volts. So I get a 3 volt drop with this side being larger than this side. Okay, high voltage over here, low voltage over there. The current told me that, and I lose 3 volts across this. So this side must be 3 volts higher than this side. This side's at 2, therefore this side better be at 5 volts. Okay. So looks like with an input of 1 volt, I get 5 volts out. Let's do this one more time for practice, but I'm going to change that input over to 2 volts. Okay, let's go ahead and let's step through this, analyze the same circuit just a little faster. Okay, over here I have 0 current in or out of the inputs, therefore I have 0 volt dropped across this 2K. If this is 2 volts, this should be 2 volts. If this is 2 volts, then this should be 2 volts by rule number 2 of Opamps. Okay, now again, 0 current going in or out of any of our inputs. So I have 0 amps here, 0 volt drop across this 2K. If this is 2 volts, then this should be 2 volts. Now I have 0 volts on this side, so I have a 2 volt drop across the 2K. Current therefore is going that way. And what's the value of that current? Well, it's just going to be 2 volts divided by 2K, just using Ohm's law, 1 milliamp. All right, well, this 1 milliamp had to come from here. If you look at KCL for this node. Okay, what's my voltage drop across that 2K? Well, I have 1 milliamp times 2,000. So I have 2 volt drop across there. All right, this side's higher than this side. So I have 2 volt drop. So this must be 2 volts higher than this. This is at 2 volts, therefore this is at 4 volts. Okay, I have 4 volts now. Ground over here, current's going down through that 2K. So I have a 4 volt drop across that 2K. So 4 volts divided by 2K is going to give us 2 milliamps. 1 milliamp going this way, 2 milliamps going down, so I must have 3 milliamps entering. 3 milliamps times 2K gives me the voltage drop across the 2K. So that's going to be, what, 6 volts? And this side's higher than this side. I'm at 4 volts over here, so I must be 6 volts larger than 4 volts. I'm at 10 volts. So V out is equal to 10 volts. So the 1 volt input, I'm getting a 5 volt output. If I get a 2 volt input, I'm getting a 10 volt output. Looks like I got a non-inverting amplifier with a gain of 5. Okay, so all I did was create a more elaborate version of a non-inverting amplifier. Oh, what I made was a very elaborate voltage divider. That makes sense. Okay. So this is a good example of just some problem. In fact, I used this in an exam, I think maybe last semester. Okay, so keep in mind, I will probably, actually definitely on the final, put one of these unknown op-amp circuits that there is no lookup table, that cookbook that you can open up. In fact, I think I have one of those books. Where I do. It's the op-amp cookbook. Here's an op-amp circuit. Here's an op-amp circuit. Here's more op-amp circuits. All of these just have names. Audio design with op-amps. Inverting amplifier. More cookbook op-amp circuits. Okay. Let's see. Is there... I think I'm going to go ahead and leave it there. So we did inverting, non-inverting, and we did analysis of unknown op-amps. And we also double-checked all of those previous ones with their given equations. So I'm happy with how much we've covered today. Let me go ahead and stop recording.